All right, hello and welcome. Let's get started. This is going to be our homework help video for solving using properties of logs and the natural log. Problems 1 and 2 ask us to identify the domain and range of each. Notice these are both logarithmic functions. So I can tell you the range right away. The range of any logarithmic function is going to be all real numbers. So range is always y. Y equals all real numbers. Use a double stroke R for that. Same with number 2, the range is that y is equal to all real numbers. And this is because if we think about the shape of a logarithmic graph, it extends all the way to positive and negative infinity. To negative infinity, usually along the vertical asymptote, and positive infinity just as x gets larger and larger. Now the domain is a little bit more tricky. Domain, in order to find domain, we must ask the question, what values are we not allowed to plug into our function? So with logarithms, we cannot take the log of 0 or a negative number. It just doesn't make sense. If you did like log base 5 of -1, it'd be asking the question 5 to what power equals -1? Well, there's no number in our real number system we can raise 5 to the power of to ever reach either 0 or a negative. So what we can do is just take the argument of this logarithm, the 4x minus 10, and say that it must be greater than 0. That way it will never be equal to 0 and it will never be negative. Let's rearrange this just a little bit by adding 10 to both sides. 4x is greater than 10, dividing both sides by 4, and we get a domain of x must be greater than 10/4 or 5/2 or 2.5. Try the same thing over here. 2x plus 10 must be greater than 0. Subtract 10 from both sides. 2x must be greater than -10. Divide both sides by 2. X must be greater than -5. And that's our domain for this problem. As a handy bonus, when we calculate for this, that number also is where our vertical asymptote is located. So in this problem, there'll be a vertical asymptote located at x equals 5/2, and over here there'll be a vertical asymptote at x equals -5. Let's move on to some solving problems. Solve each equation, round your answer to 4 decimal places if needed. A lot of these come out as whole numbers. Let's find a challenging one. I believe I did 5 in class. So let's do number 6. Number 6 uses an interesting property of logs. I see that these are both log base 7 on the left-hand side here. That means that I can combine them. Because we have addition between the two logs, that means I'm going to multiply their arguments. So this should become log base 7 of the quantity x plus 16 times x. This equals log base 7 of 17. Now that we're at this point here, the log base 17, log base 7 on both sides can actually be canceled out. What we could do 7 to the power of each side, and that would cause these to cancel. But I think it's pretty obvious. If it's the exact same on both sides, then these arguments must be equal for this whole thing to be equal. At the same time, I'm going to distribute that x to the x plus 16, and I'm going to get x squared plus 16x equals 17. Subtract 17 from both sides. X squared plus 16x minus 17 equals 0. Let's see, how do we factor that? I'll factor it over here. It's going to be, to get a -17, we need a -16 and a -1. And this gives us the values x equals 16 and x equals 1. 16 is a fine answer. It doesn't cause us to take the logarithm of 0 or negative. 1 is also a fine find an answer, we don't have to take the logarithm of 0 or a negative number, so neither of these are extraneous. Let's try, I guess, number 8. Again, it's addition, meaning that we multiply the arguments, so now we get log base 8 of x squared plus 3 times 2 equals 1. And this becomes log base 8 of 2x plus 6, that was x squared, equals 1 after I distribute that 2. Now at this point, I need to rearrange into exponential form. I can do the swoop if that helps me, but essentially the base of the logarithm becomes the base of the exponent. The number on the other side becomes the exponent. And the argument gets isolated over here. I'll subtract 6 from both sides. 8 to the 1 is just 8, so then 8 minus 6 is 2. 2 equals 2x squared, divide by 2, divide by 2. X squared equals 1, square root, square root. And we're going to get that x equals 1 or x equals negative 1. And those are actually both good answers. Neither cause me to take the square root of a negative number. The squared here makes this back into a positive, so we get 2 answers for that as well. Let's see, moving on to the back side. Here we've got equations that start in exponential form. We'll be able to use logarithms to solve these. These are problems that we're probably going to have to round to a decimal because in these types of problems, they generally don't work out to be an even number. We just need to give the decimal value, and that's going to be fine. So I divide both sides by 3 and number 9. You get 15 to the 8v equals 50 thirds. What is that? 50 divided by 3, 16 and 2/3. I'll just leave it as 50 thirds. It'll be easier to work with. At this point, our exponential part of this equation has been isolated, so we're ready to rearrange it into a logarithm. So we get log base 15 of 50 thirds equals 8v. Log base 15 of 50 thirds is equal to 1.0389. I'm just going to leave that in my calculator and divide it by 8, and then round this number to 4 decimal points. So not rounding until the very end. 0.1299 equals v. Let's see if that's right for number 9. 1299. All right. Let's go over how to plug this into our calculator real quick. If you've got an older calculator where you can't edit the bases directly, to do this, I need to calculate log base 15 of 50 thirds. So what I'm going to do is I'm going to do log of 50 divided by 3 divided by log of 15. So this is our change of base formula. I've changed it into base 10 by doing log of the argument divided by log of the base, and I get that same number that when I divide it by 8, I get my correct answer for V. All right. I think that should be good for those problems. They do end up as decimals, which kind of worries people sometimes. Let's do some from here where we're going to solve for x, but we're not going to simplify our answer. If at any point we need to use e, we're just going to leave it as e and not use a decimal approximation. So to do 13, I want to get this natural log by itself, so I'm going to add 3 to both sides. get ln of x plus 2 equals -1. The base of this logarithm is e, so when I go to rearrange it into exponential, I'm going to get e to the -1 equals x plus 2. Subtract 2 from both sides, and we get e to the -1 minus 2 equals x. This is a fine answer. We can leave it like this. To get the answer that's in the answer key, they do a little bit more work. They combine these two values into a single fraction. E to the -1 is the same as 1 over e. And -2 is the same as -2e over e. Those e's will cancel out. This here gives us -2e plus 1 all over e. That's the answer in the answer key. This answer is fine. This is a fine answer. Being able to get here will serve you just fine on any test or quiz about this material. Let's see, we'll do 15 and 16. Let's see, I'm going to subtract 5 from both sides. ln of x minus 7 equals -2. E to the -2 equals x minus 7. X equals e to the -2 plus 7, which I believe they turn into, so this is a fine answer for number 15. I believe they turn this into 1 over e squared plus 7e squared over e squared, which equals 7e squared plus 1 over e squared. If you ask me, I think that that's more complicated than this answer here. Just wanted to show you how to be able to get to that. Yeah, 7e squared plus 1 all over e squared. This one here, we'll use a little property of logarithms to get started on it. We're adding two natural logs together so we can multiply their arguments. This here is going to become ln. When I multiply that 6 to the 4x into the 1, I'm going to get 24x minus 6 equals 3. So e to the third equals 24x minus 6. Add 6, add 6. E to the third plus 6 equals 24. X divided by 24 divided by 24. Here's our final answer. E to the third plus 6 all over 24. E to the third plus 6 all over 24. All right, I went ahead and threw some examples of expanding and condensing onto this homework just to keep that fresh. Let's go through both of these. I see that I'm multiplying the w and then this radical term here. So I can split that into two logarithms that are being added. So log base 9 of w plus log base 9 the square root of u times v. This square root can be rewritten as the exponent 1/2, and then written in front of this exponent here. So this here is going to be log base 9 of w plus 1/2 log base 9 of u times v. All right, and now this can be split up into addition, and that 1/2 comes with the logarithm each time. So log base 9 of w plus 1/2 log base 9 of u plus 1/2 log base 9 of v. That we did there. Okay, I see in the answer key, instead of writing a coefficient of 1/2, they divided these terms by 2. That's equivalent in my book. So I'm just going to leave it like that. We'll just do 18 and then call it good. I got to condense this into a single logarithm. These coefficients need to become exponents on our variable. So this is going to become ln a to the third plus ln b to the fifth. Now that these are being added, we want to multiply them to write them with a single logarithm. So this becomes the natural log of a to the third times b to the fifth. And we're done with that. All right, let's call that good for this homework. Hopefully we're using this to study up for that test on the 26th. Have a good rest of your day. Bye.